similar to the ACS and such as much as I could. I haven't uploaded it, so what I'm going to do is upload it afterwards, with all the answers already on it and the explanations, so you can find it on the Study Union page. But yeah, I mean, other than that, we can just go ahead and get started. It'll be pretty painless. Your ACS is 55 minutes or so. So let's try to make it, similar. Not the ACS, surprisingly, it doesn't have a lot of math. It's very conceptual exam. So yeah, let's go ahead and get started. All right, cool. So yeah, and obviously since it's just you, at least for now, we'll just go at your pace, 100%, no rush. Yeah, of course. All right. So yeah, looking at number 1, feel free to look over that, and then we'll talk about it once you've read it.
I actually printed out old ACSs, and the first 2 were on.
The first 2 what?
The first 2 questions were on there. I picked out the 2015 one.
Like these questions?
Yeah.
Oh, nice. Okay, so do you know how to do this one?
It's the first one is B, right?
Okay, how would you go about doing this one?
Okay, well, it took me forever to do this, but once you balance it,
Okay.
it ends up being two moles of the C6H6 and then 15 of oxygen, right?
All right, yeah, so nice. Let's just go ahead and do it then. Hey guys. All right, yeah, so we'll just start in 30 seconds. All right. Okay. Chem 1B. Close. 1 semester off. All right, so Chem 1B? Are you here for Chem 1B? Okay, cool. All right, so yeah, this is the review we're going over. So right now we just started number 1. So, we're just going to go through it, 25 questions or so. And yeah, let's go ahead and do it and try to get all the explanations for it and such. All right, so you said for number 1, we just want to draw the formula. So we have C6H6 reacting with oxygen to form CO2 and H2O. Cool. So let me get the brightness on there we go. All right, so yeah, looking at that one, if you were to balance it, what would be the coefficients? Because you can't just assume any equations are balanced for you. So go ahead and try to balance that for a few seconds or so. And if you get it, just say it out loud, and then we can compare our answers. If you got one, you can just say it too.
I mean, I did it yesterday, but it honestly took me 20 minutes.
To balance it? I know, that's the thing. Balancing is one of those things that it still takes me a while to balance. So it's it doesn't get a lot faster. Yeah, what is it?
I got so it's 2 in front of the C6.
Okay.
And then 15 in front of O2.
Cool.
And then 12 in front of CO2.
Awesome.
And 6 in front of H2.
All right, so then we would have balanced our equation and gotten those coefficients there. And then, yeah, so here we're just going to apply a concept, how much O2 is required for the complete combustion of 1 mole of C6H6. So we have 1 mole of this compound here. So to solve this one, do we need to do a lot of math here? What do you guys think? No, what kind of thing are we going to be using here in order to see how much O2 is required?
You just divide by 2, right?
The 15 you divided by 2, and why would you do that?
Because there's 2 of the C6H6, 15.
Okay, yeah, so that reasoning is awesome. So essentially, but just looking at the formula, it can be read as saying 2 moles of C6H6 will make 12 moles of CO2 and 6 moles of H2O, and same can be said for 15 moles of O2. So if we have 2 moles, we need 15 moles of O2. So if we have 1 mole of C6H6, we only need half of 15 moles of O2, which is what? What's half of 15? Awesome. So 7.5 moles of O2 is what you'd require to fully combust the C6H6. Does that reasoning make sense with you? Yeah? All right, awesome. So just as you guys are going to be coming up on your ACS. It's like a lot of the problems are just kind of being able to think about things like that. Because this problem, you could potentially try to solve it using like stoichiometry with like all the math, but you start running out of time because it's a 55-minute test. So they're really testing the concept here. So if there's anything that doesn't make sense, just at any point, go ahead and say it out loud, and then we can cover it. Bless you. So formula for terbium phosphate is TbPO4. The formula for terbium sulfate is what? So in this case, we definitely want to be able to solve a problem like this. If you guys remember back from Chem 1A, when you guys had to memorize all the polyatomic ions for that one specific quiz or test, in this case we have TbPO4. So this does require that knowledge. So in this case, PO4, what's the name of that? What is the name of that anion, PO4? Nice. So that would be phosphate. And does anyone remember what charge phosphate has? Phosphate ion. I know this is like Chem 1A, so this is a while ago. So we'll go ahead and try to make it stick right now. It's PO4 3-. So phosphate is PO4 3-. And that's just something to, you guys can go back and before your exam, try to memorize, like, it's like about 14 or 15 anions, or yeah, just ions in general. So you got stuff like phosphate, phosphite, sulfate, sulfite, if you guys remember that kind of stuff. But luckily, since you've already learned it, going back over it the second time should be a lot less painstaking. So PO4 3- is phosphate. And if we look at the molecular formula here, or the formula right here, TbPO4, does that have any does that have any sort of charges on it or anything? What does it look like? Do we have any subscripts? How many TBs do we have? How many terbiums are in this formula? Yeah, just the one. And then how many phosphates do we have in this formula? Yeah, so it's one phosphate because it's one PO4. So if we have one terbium and one phosphate, that means that it takes one terbium to cancel out the 3- charge of the phosphate. So essentially that's like saying we have terbium 3+ for our phosphate 3-. Since we just have 1 and 1 of each, that means that the terbium has to have a 3+ charge in order to cancel out the 3- from the phosphate. Any questions about that?
Yeah, like, how do you know the charge of terbium? Like, I know, like you could know it that way, but, like, is there a way, like, on the periodic table, like, are all the ones in, like, that row?
Is it a transition?
Yeah.
So yeah, so when it's transition, you cannot have any defined way of figuring that out. So this problem relies 100% on you knowing phosphate.
Wait, it's, like, in the bottom thingy, like, I forgot, are these transition ones?
Yeah, yeah. So yeah, exactly. So when you look at a periodic table, it's like in the middle ones, those have no reliable way to find out what charge they have because they can have several. So in this case, you have to know the phosphate in order to find the terbium. Yeah. And so just like real quick, just as another quick refresher, so that's phosphate. Anyone remember what phosphite would be? Just to write it down. So phosphite, what would be the formula for that? So if phosphate is PO4 3-, what would phosphite be? Take a guess. Just try. What do you think would change? Does it still have the P? Because it's still like phos, right? So it's still got the P. So you can think of it that way. So it's for sure still P. Now, how many oxygens do you think it's going to have? More or less if it's phosphite? Less? Okay. How many less do you think? Luckily, this part makes sense. It's just one less. So that's all you have to think. So it's literally PO3, 3-. So it's the same thing, but it's now one less oxygen. So, but once again, like there's no set way to be like, oh, phosphite. That means that it's got this and this and this. It's about memorization for these. I wouldn't expect a lot of questions like that on the ACS, but you don't want to miss those like 1 or 2 when you can just memorize these before the exam. So now that we know that terbium has a 3+ charge, it wants to know the formula for terbium sulfate is what? So in this case, like we said, terbium has what charge? So if terbium has a 3+ charge, now it requires us to know what is the charge of sulfate. So in this case, if phosphate is PO4, what do you think sulfate is? Nice. So sulfate is SO4. But what difference with sulfate is it's not SO4 3-, it's SO4 2-. So, and once again, it comes down to memorization. So we have these two molecules coming together, a terbium and a sulfate. Anybody know how we could get the formula out of that information displayed right here? Nice. So we bring this 2 down to the terbium and the 3 down to the SO4. So we end up with Tb2 SO4 3, and that's like the simple way to come up with a formula. So what answer choice would that be? C? Awesome. All right, so any questions about that one? So did the concept from that make sense other than memorizing the ions? Cool. All right, so any questions before moving on to number 3? No questions? All right, so how many moles of hydroxide are there in 2.5 moles of magnesium hydroxide, or MgOH2? So this is drawing on that concept as well. So right here, if we have 1 mole of MgOH2, the molecule given to us, if we have 1 mole of that, how many moles of OH are there in 1 mole of MgOH2? Yeah, so if you have 1 mole of the molecule given to you, MgOH2, how many moles of OH do you have in that 1 mole of MgOH2? 2, nice. So, because every 1 molecule has 2 OHs, right? So 1 mole of that equals 2 moles of OH, as far as we're concerned. So does that make sense? That's like saying how many pepperonis are in 1 pizza, right? Just because the pepperonis are part of the pizza doesn't mean it has to be 1. You could say like 8 pepperonis in 1 pizza. So here you have 2 OHs in 1 MgOH2. Yeah. Yeah, essentially you get the 2 because it's, yeah, there's 2 OHs. And so that's how many moles there are if you have 1 mole of this whole molecule. So yeah, the subscript would be telling you in this case. All right, so now what it's telling us is we have 2.5 moles of MgOH2. So if we have 2.5 moles of the entire molecule, what do I have to multiply my 2 moles of OH by? Nice. So 2.5 times 2 gives you what? What would we get as our answer? 2.5 times 2. 5. So then we would have 5 moles of OH in this case. Answer choice D. So this kind of wording, this kind of speaking on the exam is really common. So you guys just want to be able to identify moles and such of a molecule as well as the specific atoms and such in a molecule. So for example, just to further clarify, in 1 mole of this molecule, we have 1 mole of Mg and 2 moles of OH. You could say, oh, I have 2 moles of oxygen, 2 moles of hydrogen, etc. It's essentially how many are there in that compound, and that's how many moles there are in 1 mole of that compound. Does that make sense? So you just want to kind of think through things this way. Try to take a less mathematical approach and more of a conceptual approach. So any questions before number 4? Mm-hmm. Yeah, good question. All right, so number 4, barium chloride reacts with sodium sulfate according to the following equation. So first things first, I'm just going to write the equation right here to make it all one thing. Okay, so that's the equation they gave us. First of all, is that balanced or no? Got a yes? Okay, like reasonably. It looks pretty balanced, yeah, so that one would be balanced. Just make sure you get in the habit of checking every equation, because some might look balanced, but they're not. But in this case, yes, it is balanced for us. And then they tell us a student mixes a solution that has 10 grams of BaCl2. So let's just go ahead and write down that information that's given to us. So
Is there like a fast way of like knowing if it's balanced or not, or do you kind of just have to like check it?
personally, like what I do is, yeah, I have like a two-step way of checking. I look if they have if it already has like a coefficient somewhere, it's pretty safe to assume they balanced it already. And if it's all blank, then that's when I check. Yeah. Hello. All right, so we have 10 grams of Na2SO4. And we have 10 grams of BaCl2. All right, so just writing down kind of what's given to us. And then, so here's the part where, if you guys remember from Chem 1A, one of these two reactants, because we have two things reacting together, one of them is going to be our limiting and one's going to be our excess reactant. Do you guys remember that a little bit? So we got to determine which one's which in order to see how much product we can actually make. So luckily, there's like a quick way to do it that we can focus on for now. So do we have the same amount, do we have the same mass or different mass of reactants? Same. So we have 10 grams of both of them, right? So in this case, we want to see what is the mole ratio between the reactants and our product. We're not worried about NaCl because we're making BaSO4. So if that's the one we're worried about, do any of these have a coefficient in front of them? Are there any coefficients here? Because if not, that means that you're essentially saying 1 mole of BaCl2, 1 mole of Na2SO4 will just give you 1 mole of BaSO4. So it leaves the problem it leaves you with a lot less things to worry about. So if they're all like 1 mole to 1 mole to 1 mole, then essentially what you can do is this. Notice the problem tells you the solution has 10 grams of BaCl2, and that M right there, it has the molar mass of 208.2. So molar mass equals 208.2 grams per mole. So it tells you the molar mass of that one, and then it tells you the molar mass of BaCl2 is, oh, excuse me, I wrote that in the wrong spot. So that's the molar mass for the one under it. All right, but it tells you then the molar mass of BaCl2, as we said, is 208.2. And the molar mass of Na2SO4 is what? Find in the problem. What's the molar mass of Na2SO4? Yeah, exactly. Pretty much, their atomic masses together. You add them together, but in this case, yeah, they happen to give it to you. So what do they give you? So you don't even have to take out your calculator. Nice. 142.1. All right, so they give you both of them. So if you guys just remember a quick conceptual check, molar mass is essentially how many grams do I have in 1 mole of that compound. We all agree, does that make sense? Is how many grams we have in 1 mole of the compound, right? So if I were to ask you, in 1 mole of BaCl2, how many grams do I have? What would it be? Yeah. How many, in 1 mole of BaCl2, how many grams would I have? Yeah, nice. 208, because that's our molar mass. So essentially, in 1 mole of it, we have this many grams of it. All right? And so, as you can see, different compounds have different amounts per mole. That's why we have different molar masses, right? So what we want to look at here is which one of these do we really have more of? Because you'll notice that for this reaction, it's 1 mole of BaCl2, 1 mole of Na2SO4, and that gives you 1 mole of BaSO4, right? It's like everything's 1 mole. So which one do we have more of to complete the mole? Do we have almost a mole of BaCl2 or almost a mole of Na2SO4? Which one do we have more of? Because how many grams do we have of each one? 10 grams. But they both have different molar masses, right? So 10 grams is closer to which one? 142 or 208? 142. That means that we have more moles of Na2SO4. Why? Because 10 grams is closer to 1 mole of it. Think of it like hydrogen. What's the molar mass of hydrogen? Who remembers? 1. So if we have 10 grams of hydrogen, how many moles do we have of it? 10, right? So we would have 10 moles of hydrogen in this case. So in this case, what we have is 10 grams of both of them, but 10 grams is more compared to 142 than 208. So we have more moles of Na2SO4. Does that make sense? So then that means that we have less moles of which one? BaCl2. So if we have less of BaCl2, does that mean that it's going to make more product or kind of determine how much product we make? Yeah, so that's the one that's going to determine how much product we make. What do we call that reactant? Awesome. So that would be our limiting reactant here. And it's important to determine which one's the limiting, because if it's going to ask us what's the percent yield, we're going to have to do a calculation. But we know we're going to want to use 10 grams of BaCl2 because it's going to make less product. Because we can't use 10 grams of Na2SO4 because we don't have enough BaCl2, because we don't have the same exact amounts.
If it wasn't like the same amount of grams and like you kind of have to figure out like how many has more moles like itself, you just do 10 divided by how many grams.
Yeah, if it, like instead of 10, whatever they gave you, yeah, exactly. You'd see which one has a higher one, and that would be the excess, and the lower one would be the limiting. Yeah, good question. So BaCl2s are limiting. So in that case, if we're looking for percent yield, what formula is the percent yield formula? Percent yield equals what? Remembers? And then using the words theoretical, actual, how would I make that formula? Awesome. So actual over theoretical. So how much did we produce over how much could we have produced under perfect conditions where there's nothing lost? Does that make sense? So just remember actual over theoretical. They're alphabetical, A and T. So luckily, if you forget, just try to think back to that. So right now in the problem, which one of those do they give us? Do they give us actual or theoretical? What does the problem give us? An actual yield or the theoretical yield? Yeah, so try to read through it and see which one does the problem give to us. Huh? Nice, they give us the actual because they tell you they obtained 12 grams of BaSO4. So they performed the experiment and got an actual value. So us sitting here at home or whatever, we don't have an experiment set up. All we can find is the theoretical. So think of it like that. If we're doing math instead of actually doing an experiment, we can only find the theoretical amounts. So to find theoretical, we know we start with how many grams of BaCl2? 10. So to do the math, we know we have 10 grams BaCl2. And we have to go from grams of BaCl2 to grams of what? Awesome. So we're going to have to go all the way from grams of this to grams of that to see how much product we can make. So 10 grams of BaCl2. So down here, to cancel out the grams, what would I write? Nice. The molar mass of BaCl2, which we said was 208.2. And that's how many moles? So that's 1 mole. So now we're going to our stoichiometry. And so here now we say we canceled out the grams of BaCl2. Now we have 1 mole of BaCl2 up here. So how many moles do I have in the equation of BaCl2? Yeah, it is 1. Awesome. So we know that 1 mole now of BaCl2. How many moles of BaSO4 do we have? Also 1. So their mole to mole ratio is what? Yeah, it's just 1. So in this case, it doesn't affect the problem. But you know, some problems, they will have it affect it when they're not all just 1. So 1 mole of BaSO4, and then to go from moles of BaSO4 to grams, what do I have to multiply by? It's the what? So I know I want to cancel out the moles down here. So in 1 mole of BaSO4, what do I have? Nice. The molar mass of BaSO4, which is given to us to be 233.2. Awesome. So 233.2. And so go ahead and do that math. Make sure you guys are still comfortable using your calculators for these kinds of problems. And let me know what you guys get. Yeah, go for it. No, so this I'm going to be posting it afterwards with all the answers on it.
Oh,
Yeah, but on the page, I just have like some practice exams posted right now, but this is the one that I'm going to be posting with the answers. Yeah, yeah. Yeah, anyone get an answer for our theoretical yield? 11.2? 11.2 grams. Awesome. So I just said it, so I'll just write it. It's the theoretical yield. So that's how much you can theoretically get under perfect conditions. So they performed the experiment and got how many grams? They got 11? 12. So they got 12 grams. That's where it tells you here. They obtained 12 grams of that. So that means that in this case, they got more than what you can actually get. So let's double check that math there real quick. Are we all sure about 11.2?
Oh, no, that's just what I got. That's why I asked.
I feel you. No, I make mistakes all the time. Yeah, go ahead and try it out, everyone. Yeah, what's up? How would you work it? Okay, so in this case, you would do 10 and then multiply all the top stuff together and then divide by all the bottom stuff. So essentially, you would multiply all the top ones and then divide everything by 208.2.
I got 11.2 as well.
Yeah? All right, so 11 point.
10 grams multiplied by 233.2 divided by 208.2.
Yes. Yep, that'd be it.
Yeah, so I got 11.2.
All right, so let's go ahead and keep that. So how much? So if we got actual over theoretical, our actual yield was 12 grams, right? 12 grams over our theoretical. You know, just to go with the problem, theoretical is what?
11.2.
Yeah, 11.2 grams, leaving us with an above 100% yield, which obviously this problem is pretty wonky. So you would work it this way. I mean, I don't know what to say. That's frustrating. But yeah, so we end up with over a 100% yield. Realistically, that's not something that would ever happen. But you would want to work it out the exact same way. And then ideally your problem wouldn't mess it up. All right, so any questions about any of the concepts here? Are we all comfortable with like defining what is your theoretical yield? What is your actual yield? What is a percent yield? All that stuff?
So actual is just actual is experimental, theoretically calculate.
Yeah.
What's percent yield?
So percent yield is essentially saying how much of your, like essentially, you performed the experiment, how much did you actually get? Yeah, there you go. Out of what you could have gotten. But yeah. A big part of this one is being able to find your limiting reactant. So make sure you work through at least one or two of those problems before your actual ACS exam, and then you should be fine. They're all essentially the same. So once you can find your limiting reactant for one problem, you'll be pretty much set to find them for other problems. When? Yeah, what? Yeah. That is the final. It's like a standardized exam, but it's not actually standardized. But they do give you 55 minutes, and then they give you the exam, and then it covers like Chem 1A and Chem 1B material. Yeah, I know. I feel you. But on the bright side, well, on the potential bright side, is like some professors are like kind and like I don't know how it'll go. Obviously, it's different with every professor, but in my history, having seen it administered. Some will curve it, some will take some questions out that they don't find fair, that kind of thing. So, it just depends on the professor, so. Well, yeah, we'll see. But yeah, any questions about this one? No? All right.
So above 100% is not possible.
No, it's literally impossible. Yeah, there's got to be a calculation error. But yeah, so obviously when I post the actual answers, like I'm going to double check, make sure every little number was written correctly. There's got to be some kind of calculation. I mean, it can't be 100%.
Because as a rule, actual will always be less than theoretical.
Got 10 over 208.
Wait, isn't 12, is this 12 not on the,
Yeah, I almost switched them. 12 being like theoretical.
is that not on the,
No, because I told you they obtained that. So in that case, yeah, I mean, it could potentially be the problem having weird numbers, the way I typed it up or something, but yeah, just so that since we have a limited time, I don't want to spend time like troubleshooting that. So when you guys get the answers, I'll have an explanation if it wasn't the problem.
wait, is the answer C?
C?
Yeah. You have the answer right now.
Yeah, no, in that case, I don't have the answer. Is it C?
Well, I mean, if you switch them, it's C.
I mean,
11.2 over 12.
yeah, I mean, you shouldn't really be switching them. So that's because like it is actual over theoretical, and they perform the experiment. So it has to be theirs has to be the actual.
Actual though is the one that you actual. Never mind.
I know. It's easy to like have your like opinion switched on it, but just stick with like what we said so far, and then in the problem
Like
it's
whatever, if they have an example of someone doing it, that'll always be the actual.
yeah, that 100% yes. Yeah. All right. So trying the next problem here. All right, so a lot of this is multiple choice, so go ahead and think about it. Which of the following is an exothermic energy? Go ahead and look through the answer choices, and then if you find one that you believe is correct, go ahead and just say it out loud. What is it? Yeah, so which one is an exothermic energy? So exothermic means what happens to the heat? It's released or it is absorbed? Okay, so releases heat. Yeah, exactly. Releases heat into the surrounding. So essentially, we want to see which of these energies release heat. So let's think about it. You think it's what? D? Yeah. All right, so we got an option for D here. What else? Anyone else think D? Anyone agree, disagree? You agree? All right, cool. So we got peer pressure setting in. Anybody else think it's D now? All right, let's think about it. Yeah, let's think about what these even mean. Because this was like first test stuff, I believe. Ionization energy. That's the energy required for what? Who remembers ionization energy?
That's the energy required to either remove an electron or gain an electron.
Okay, so which one is it?
I think it's gaining an electron because to become.
Think it's gaining? Well, then what would electron affinity be?
I feel like affinity is like wanting.
Yeah, so that one,
Would be gaining
There we go. Nice. So this one is gaining an electron, energy to gain electron. And then this one would be energy to lose an electron. All right, so, oh, and then breaking a lattice. So who remembers what a lattice is? It's what? It's a structure. What kind of shape is it? Yeah, there you go. It's like a cube. It's formed by ionic compounds coming together. So it's like the lattice is a bunch of ions in a cube, essentially, right? So breaking a lattice, and in this case, let's focus on A and B, because obviously they're opposites, right? So one of these kind of has to be one, while the other one has to be something else. So what do you guys think? Electrons have what kind of charge? What kind of charge do protons have? Positive. Do you think they attract each other or repel? Okay, so I got two different answers. Yeah, opposites attract. So positive proton, negative electron attract, right? So my first one is energy to lose an electron. So do you think I need to put in energy to separate two things that are attracted to each other, or do you think that they're happily going to separate? You need to put in energy. So if you're putting in energy, is that endothermic or exothermic? Endo. You're putting in energy. So just think of it like that. They attract each other. So to pull them apart, they're kind of going to resist, so you're going to need to put in energy. Now, electron affinity, energy required to gain an electron. If you're going to put an electron near a positive proton, do you need to put a lot of effort into making them attract each other?
No.
So then what do you think that would do? It would release energy, so that would be your exothermic energies, your electron affinity. So think of it like that. That one would happen normally. That's another way to talk about exothermic, is something that happens spontaneously. Put a positive and a negative together, spontaneously they're going to come together, right? So, and then in the case of all of these, you can just remember that those are all endothermic processes, A and C are. And then A, we talked about why. As far as breaking a lattice, think about it. You're breaking up a cube structure with a bunch of ions that attract each other, right? That's going to require some energy. It's not something that's going to happen spontaneously, right? But yeah, so electron affinity is actually like the only exothermic one that you guys really learned. So if you just kind of remember that one as being exothermic, you should really be pretty good. Any questions about that? Definitely just remember what they mean as well. So ionization versus affinity, that kind of stuff. All right. So number 6, a little question back from from Chem 1A. What volume of water would be required to dilute 15 milliliters of 4 molar HCl to 3 molar HCl? What kind of formula would we use here? Awesome. M1V1 equals M2V2. Awesome. So M1 in this case would be what? 4. Nice. So we got 4. And what's my V1? Awesome. So 4 times 15 equals, what do they give us? Is 3M or M2 or V2? Good question. So if you don't convert to liters, just understand that your volume that you get will be in milliliters as well. So you don't, as long as you keep it consistent on both sides, you can use whatever you want. Cool. So M2 would be 3, and V2 is what we're looking for. So then it turns into that typical problem with one missing variable. So then what would you guys get for V2 in that case? What was it, 20? 20 milliliters. Awesome. So M1V1, M2V2, that formula luckily kind of flows. So just remember that one for the exam. You could always get your dilution problem.
It's only dilution that you use that one for?
Yeah, exactly.
Okay.
Yes. Good question.
But it has to say volume too.
It has the what?
Does it have to say volume also?
Volume? Yeah, you need to have both molarity and volume for this one, yeah. Yeah, no, good questions. All right, so any other questions about that one? All right, looking at number 7, a sample of 54 grams is heated from one temperature to another. How much heat is required? What's the symbol for heat? Huh? Not delta, but there you go, Q. I know those are all kind of meld together. So that's from back Chem 1A. We know Q is heat. Now, what is the formula for Q? Nice. M cap. Awesome. So in this case, M stands for what? Mass. C stands for what? There you go. Yeah, specific heat capacity, which they give us. And then the delta T is the change in temperature. So let's go ahead and plug everything in. So my mass is what? Awesome. So 54 grams. What's my specific heat capacity? Very nice. 2.48. And then in this, do we know what the change in temperature is? Yeah. No, for these problems, good question. Anytime you have a change in temperature, you can leave it in Celsius or you can do it in Kelvin because they follow, like if you raise 1 Celsius, you also raise 1 Kelvin. So any changes are the same. So essentially, in this case, you would not have to convert to Kelvin. But one thing to add is delta means change in, right? So that means we subtract what from what? Do we subtract the final from the initial or the initial from the final? How would I? All right, so 1340C, do we all agree with that? I mean, that seems reasonable. Anyone disagree? All right, cool. So 1340. So that means that do we need to put in heat or does it release heat? So well, first of all, there's 2 ways to think about it. Is our Q positive or negative? So is that exo or endo? So positive is exo? Endo. Positive is endo. Does endo mean we put in heat or it releases heat? Put in. So we put in heat. Yeah, exactly. So you put in heat, and now we can look at it the other way is, did the water get hotter or colder? It got hotter, so you have to put in heat to make something hotter, right? So that's like the other way to realize that it's an endothermic process. You have to put in the heat to heat up the water, right? Yeah, what's up? Yeah. Well, as far as, yeah, if it's like for this particular problem, yeah, it'll always be endo. Awesome. All right, so any questions about that one? All right, so moving on to number 8, a little bit of enthalpy change. I saw this on the ACS from like over summer. They had a question just like that with the A's and the B's, etc. So we want to make sure we know how to solve it, because I know we've all done the whole enthalpy, what is that even called? The Hess's law problems like this one with numbers and with real equations. So now let's make sure we can do it with just the variables, because keep in mind, they don't want you to do a lot of math because it's a timed exam. They want to make sure you just apply the concepts. So over here, it wants us to end up with this formula here. 2a plus b plus d yields 2f. So we got to manipulate these equations by flipping them, blah, 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 etc., until we get to our desired solution. So let's start from the beginning. We want 2a. So first equation, does that have an a? Is that in the right side? Is it supposed to be in the reactant side? Yeah, it is. So in this one, do we look like we have any reason to change our first one? Well, because then we want to look at our second equation. Does it have an A? So then maybe that's where we could get our second A. So is that A in the right side? Awesome. So do we really need to do anything to that one? Did we account for 2 A's on the reactant side so far? All right. So far we haven't had to change anything. Let's move on to the B right here. So it's 2A plus B. Do we have a B in any of our equations? The first one, is it on the correct side? Okay, so do we need to change it? So far, would we say that we've accounted for a single B on the reactant side? All right, so far we haven't had to change anything. D, do we have a D anywhere? Second equation, is it in the correct side? It's not, do we need to flip it? So we need a D on the product side? All right, cool. So we all agree with that? All right, so multiply by -1, because we need a D on the product side. Is this D on the product side down here? All right, yeah, so it's not on the product side. So do we need to multiply by -1? Cool. So we accounted for the D on the reactant side like we needed to here. Now we move on to the last thing we need, 2F. 2F should be on the product side. We look over here. Do we have any F's anywhere? Just on the last one here? And also this one up here, right? How many F's do we need? 2. We have the 2 F's. We know that, is the top one on the correct side? Is the bottom one on the correct side? So what should we do? Awesome. So we multiply this one by -1 to flip it. So essentially, now that equation turns into E plus C gives you F. By multiplying it by -1, so positive 15 turns into what? Nice. So that's now -15 kilojoules per mole or whatever. All right. So now let's go ahead and look through and make sure that, oh, and this is Ne, by the way. C plus E yields F on this equation there. All right, so now let's go ahead and look and see if we've got this equation. So do we have 2A's on the left in these equations? Do we have 2A anywhere? All right, so we've got 2A. So far, so good. Do we have 1B on the left side anywhere? Yes, we do. So we got the 1F at the top. Do we have a singular D on the left side? Sweet. And then 2 F's on the right side. Do we have that? Awesome. What can we cancel? The C and the E's get canceled. We don't need those. So those all cancel out because they're on opposite sides. All right, so now that we essentially manipulated all the equations to all end up giving you this, essentially, when you add them all up together. So if we added up all these equations together, what should we do with all these delta H's? Add them. Now you just got to make sure that you account for any changes you made. So we changed that one. So we do -35 plus 20 plus -15. So we get -30? Awesome. So -30 would be our final answer. Do we all agree with that? Awesome. So these problems right here, like I said, I've already seen it on the ACS. And it's got the A's and the B's and the C's and the D's, etc. So definitely try to manipulate your way around these. Because I know when you first see them with just letters, they can be pretty tricky. So it's good to be exposed to those beforehand. Any questions about that problem? No questions? All right. Number 9, what is the oxidation number in the carbon in formaldehyde, which the equation's given to you right there. So go ahead and try that one out. Find the oxidation number. This is back from Chem 1A as well, but it's a very important concept. And if you get an answer, feel free to let me know. We can all compare. Anybody get something? No? Yeah, I know. What has it been, like months since we did oxidation numbers? Luckily, there's a pretty simple rule to follow. We know that hydrogen tends to form what ion? Positive or negative? Positive. And positive what? What was it? Positive what number? How many electrons does it have? 1. Yeah, so it'd be positive 1. So hydrogen tends to form a positive 1 ion, right? So for oxidation numbers, when you're calculating oxidation numbers, whenever you see an H, it's going to be +1. And whenever you see an oxygen, what ion does oxygen tend to form? Who remembers? Negative, yes. Negative what? 6. Not 6. So what's the magic number that you have in a shell? 8, right? If oxygen has 6, that means it needs how many to get 8? So if it gains 2 electrons, it gains what charge? Positive. If it gains 2 negative electrons? There you go. There you go. So it'd be -2. So oxygens are -2 each. So those are the main ones you'll see in oxidation numbers. So if we look at this one here, if we have CH2O, does this molecule have any net charges anywhere? No, right? Because if it did, it would say CH2O minus, CH2O plus, whatever, right? So we can say that the net charge is then what? Net charge of the molecule? 0. So that means that all my oxidation numbers in this molecule have to add up to 0. So if we have 2 hydrogens, each hydrogen we said gives what oxidation number? +1. So that means that we have so far with 2 hydrogens, we have how much? 2. Awesome. So we have +1 times 2 to account for the oxygens. Does that make sense? Hydrogens. 2 hydrogens, each +1. How many oxygens do we have? 1. Each are a charge of what? 2. -2. So plus -2. There you go. And then we don't know what the carbon one is, so we'll just say plus C has to equal, all of those charges have to equal what? 0, because it's a neutral molecule. And then you just have to solve the problem. So we end up with +2 -2 plus C equals 0. So go ahead and solve that one. Get some practice solving the algebra aspect of this stuff. So 2 minus 2 plus C equals 0. Let me know what you get for C.
Are they all going to equal 0?
If they have no charge, yes. But for example, if it said, if you look right there at the molecule, CH2O minus, we would have said that all this stuff up here equals -1. So you got to set it equal to the total charge of the molecule, which in this case is 0. In most cases, it's going to be 0 just because it's mostly testing the concept. Anybody get a value for C? Zero? You're a little confused?
Would it be 0?
Okay, yeah, so it'd be 0 because in this case, 2 +1 hydrogens and 1 -2 oxygens cancel each other out. So that leaves the carbon with only a possibility of having a 0 formal charge so that this all can be evened out to 0. So in that case, yeah, the carbon's 0. Keep in mind, carbon can have a +2, -2, etc. It can have whatever depending on the other stuff that's there. So you could get this question again with a different compound and asks you what's the oxidation number of carbon, and it could be a different number. So if you see carbon, don't just assume it's going to be 0. It could be anything else.
Wait, how did you know that the overall charge is 0?
Because we look at the molecule, and it just says CH2O. It doesn't say CH2 plus, CH2, etc. So if this was what's the formal charge of P in PO4 3 minus, phosphate, then we would say it all equals 3 minus. Yeah, so, yeah, of course. So any questions about that? So that's just your oxidation numbers. Mostly just remember that hydrogen is +1 and oxygen is -2, and you should be in good shape. Yeah, so there's a couple exceptions, but they would not throw those at you. Yeah. All right, so number 10, what is the value of the quantum number L? And I made it capital L just because a lowercase l looks like an I. So just picture that little fancy L that they use. What is the value for the quantum number L on a 5p orbital? Is it 3? Okay, so let's think about it. You're thinking of how many orbitals?
I think it's 2.
You think it's 2? So you're saying L equals 2. Anybody else? Let's hear it. Can I what? The quantum numbers? Yeah, yeah. So essentially, if there you go. All right, so we know it's 1. So now let's go ahead and talk about why. So if n equals 4 in this case, or it's 5, excuse me, because it's 5p. Are we all cool with knowing that n equals 5 based on them telling us it's a 5p orbital? Yeah. All right, so n equals 5 in this case. So L can equal anywhere from 0 to what?
3.
Is it 3? How does L relate to n? What is that? N minus what? 1. So L can be anywhere from 0 to, exactly. So in this case, it is 4. But if you just remember, it can be any value from 0 to n minus 1. So in this case, it tells us 5p. We know that 0 is S, as you were saying. When L equals 1, it's P. When L equals 2, it's what? D, nice. And when L equals 3, it's what? S, P, D, F. So if they tell you 5p, you already know n equals 5, and you already know L equals 1 because 1 is the same as p when it comes to the L. So if they tell you S, P, D, F, whatever, you already know L. But then, yeah, and then our ML, which is the next quantum number, the magnetic quantum number, so that can have a value range from where to where? Negative what? Negative, there you go. So, no, excuse me. So it's essentially just, if we want to make it more general, negative L to positive L. So whatever L you're talking about, so in this case, if we're talking about L equaling 1, then it can be anywhere from negative 1 to 1. Does that make sense? All right, so, and then just to try to maybe make it click a little bit more, we know that when L equals 1, we're talking about P, right? P has how many orbitals? If I draw like 3, let's just do this right here, 5p, how many lines do I draw above it to draw electrons in? Yeah, let's refresh that. It's not 6, it can fit 6 electrons, but how many orbitals is it? 3, there we go. So you guys remember how when you have a P, you have 3 lines over it? All right, so why do you have 3 lines there? Well, if you think about it, we said P means L equals 1, right? If L equals 1, my ML can be anywhere from negative 1 to positive 1. So negative 1, 0, and 1, right? How many numbers is that? How many orbitals do I have? Those are correlated. So if your L equals 2, you're going to have more orbitals because ML will go from negative 2 to 2. And then when L equals 2, what is that? Is that S, P, D, or F? When L equals 2. When L equals 2, what is that? S, P, D, or F? D. If we draw a D, right, how many lines would I draw above it? You can always just check. If I have D, that means that my L was what? 2. So my ML can be anywhere from negative 2 to positive 2, right? How many numbers is that? That's 4? Yeah, I forgot the 0. So that's 5. So D has 5 lines above it. So it would have 5 orbitals. So ML is related to that. Yeah. Yeah, because it can hold 10 electrons, exactly. All right, so essentially for this one, I would definitely expect one of those problems, like which of these sets of quantum numbers doesn't work. You guys remember those, like from your practice exams and such? So definitely brush up on the quantum number kind of concepts. But in this case, if they give you like 5p or 3s or blah, 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 they're already giving you n as well as L because they're giving you both things. Any questions about this one before moving on? No question? All right. All right, moving on to number 11 then. So let's go ahead and do a little basic, like Chem 1A concept. Which element has chemical properties most similar to those of P? So what kind of trends have the same chemical properties? Is it the same row or the same column? So I got one row. So what do you guys think? Let's all try to agree on something. Huh? AS and N are in the same column as P? All right. So S is the only one in the same row. Okay, cool. So, but what? As well? Okay, so we got like a combination here, right? So let's think about it this way. Let's try to determine first column versus row. If you guys think about a row, what side of the periodic table are metals in? The left, right? What side of the periodic table is P in? The right. So if I have something in the same row as P, and it's a metal similar to phosphorus? So can it be rows? No, because then, yeah, we'd be saying like metals are the same as like chlorine or stuff like that. So essentially that leaves us with column. So which element has chemical properties most similar to those of phosphorus? So which ones can we eliminate so far? Al and AS. So is sulfur in the same column? Yeah, so I think, yeah, you guys got a periodic table on the ACS exam. AS in the same column. Cool. Right under. All right, cool. So in this case, the main concept here is that they're in the same column. So as far as that one would go, it's any ones in the same column would work. So this one happens to have both. And that's just like bad answer selection. But yeah, so I can see how you would have deduced that. So same column, we have similar properties. Any questions about that? What's another word for column? Period. Is it period? There we go, yeah. So column goes with group, and then row goes with period. For some reason, period means row. But yeah. So, all right, any questions about that one? So just try to remember that concept. So now, which has the greatest electron affinity? Looking at these elements, F, Cl, Br, and I, what do we know is the trend for electron affinity? Which direction does it increase in? Nice. So up and to the right, it increases. So which one of those elements is up and to the right? Fluorine? We all agree with fluorine? Is that the most up to the right?
Wait, so this one is literally on the 2015 ACS, I can print it out.
Okay.
And it says which halogen atom has the greatest electron affinity.
Mm-hmm.
And I put F, but the answer is Cl.
So yeah, for that one, there's a discrepancy between Cl and fluorine having different electronegativities, but I would follow the trend for her class personally. I see what you're saying.
No, yeah, because like the answer on the ACS was not F.
Yeah,
It was Cl.
yeah, I know. That's what I'm saying. So chlorine, like this problem happened in last semester in Chem 1B as well, where the professor also just kind of said like, Cl is weird in the term, because do you guys remember the electronegativity trends?
Yeah.
It's the same trend. He said Cl technically has a higher electronegativity even though it's under fluorine, but he said for like my class it's going to be like this. So as far as that goes, I mean, like I said, it's like a weird one. So I would stick with following the trend because she never explicitly told you guys, hey, this is an exception where Cl is this. She taught you guys the trend, if that makes sense. So I wouldn't expect her to make you guys like know that fact, if that makes sense. Yeah, no, yeah, she 100% like administers it, and then she has it graded. It's not like some standardized company comes in or anything. Yeah, she has the power to do like curve it. Yeah, yeah. She can even be like, I just removed that question because I didn't think it was fair. Like it's 100% up to her. They just use it to kind of test you guys, essentially. Yeah, yeah. Yeah, so just keep the trend in mind. All right, so which of the following has no unpaired electrons in its ground state? All right, so now we go back to our whole electron configurations. If we look at them, no unpaired electrons. So essentially, since these are all very like low elements, they're like very small amount of electrons. Let's go ahead and draw all of them. So if we have lithium, how many electrons do I have? If you guys want to look at a periodic table, how many electrons does lithium have? Three? You said three? Did you say three? Yeah. Okay, cool. So it's got 3 electrons, right? So if you guys remember that whole diagonal chart, right? We know that we start out with 1s2, and then we go on to 2s2, 2p6, etc. So that's kind of the list of how it goes. Do you guys remember having to write those things in that order? So as far as this goes, these are only going to go up that far. So lithium has 3 electrons, as we said. 3 electrons. So that means that it's going to be 1s2, nice. So 2s1. So if we were to draw this 2s right here, how many electrons are in there? Is that paired or unpaired? So it's unpaired. So is that going to be our answer? So is it? So which of the following has no unpaired? So it would not be. So lithium does have an unpaired electron. Moving on to beryllium, how many electrons does beryllium have? Awesome. So 4 electrons. So that would be 1s2, 2s what? 2s2. So now we have the same 2s, right? How many electrons does beryllium have in the 2s? So that's 1 and 2. So is that paired or unpaired? That's paired, right? So does beryllium have any unpaired ones? No, right? So in this case, beryllium would be our answer because it has no unpaired electrons. Any questions about that one? So that goes back to that chart that you guys have to memorize, or not memorize, excuse me. You guys had the chart on the exam, right? Like she let you use it? The one that's like, it's the 1s, 2s, 2p, and it was like diagonally down.
Oh no, we have to remember that.
You guys have to, she didn't give you guys a chart? Okay, yeah. So definitely brush up on that one. At least for like the first couple rows of elements, you don't have to memorize the entire thing. Just for questions like this on the ACS. Okay, yeah, some professors let you use it, some don't. All right. So, which electronic transition in atomic hydrogen corresponds to emission of visible light? All right, so super technical question here. Luckily, I'll give you guys a hint. It's got like a pretty easy answer here. What's it wanting for? Emission? What's the other type of thing you can have? So there's emission and what? When it talks about emission, anybody remembers what's being emitted? When we're talking about light, what's that light particle called? Oh my gosh, that was actually a while ago, wasn't it? That was like first test stuff. Man. So when we have a light, the smallest particle of light is called a photon. You guys remember that? So when it's talking about emission means release the photon. So if you can release a photon, what's the other thing that can happen? What if a photon comes and hits you? What's the electron going to do? Absorb it. So we have emission and absorption. So absorption means absorbed a photon. Cool. So emission versus absorption. So now think about it this way. Light is a type of energy, right? So if we have, for example, emission, which is what we're looking for, right? It wants to know which of these is an emission. Emission means released a photon. If you release a photon and you release energy, if you're releasing it, are you getting relaxed or excited? Relaxed. Awesome. So essentially, emission and relaxed can be used together. So relaxed is emission, therefore absorption must be what? Nice. So excited is absorption. So let's try to make some sense of these. Like, it's a bunch of random ends and such, right? But if it wants emission, it wants relaxed. If an electron is getting relaxed, do you think it's going to come further away from the nucleus or come closer to the nucleus? Which one will it be more stable in? Closer or further? Closer. So if we want relaxed, we want an electron that moved closer to the nucleus. So which one of those answer choices shows an electron that's moving closer to the nucleus by relaxing? Awesome. A, because B is moving from 1 to 2, so that's further. C is 3 to 4, so that moved further away. And D is 1 to 3, so that also moved further away. So any questions about that? So yeah, exactly. So the main thing to really remember here is this, is that emission, just remember that means relaxed, and excited means absorption. So if it wants emission or if it wants absorption, you can look at your answer choices accordingly, because one of them needs to be moving further away, one of them needs to be moving closer. So now go ahead and for number 15, try to draw those out. The ACS, it's unfortunate, but you're going to notice that the things you do have to draw, it's like, I know we're all like cool with Lewis structures and stuff, but they always give you these weird ones that for some reason trip you up. So try to draw these two and make sure you'd be comfortable drawing something like that, because the ones that they'll give you are always either some kind of exception, it looks weird, that kind of thing, so it'll throw you off a little bit. So try to draw these two and then let me know which ones you think are linear. Yeah, so you guys have like a minute or so to try to draw them. It's important that you guys practice that as well. Just in case you can't see too well, that's NO2 plus and I3 minus. right, so I'm going to go ahead and start drawing them as well so we can kind of compare. Did anybody get a structure for NO2 plus yet? Yeah, did you? All right, so NO2 plus. What's our central atom at least? And we know we're going to have 2 oxygens on either side, right? And then this molecule has a net charge of what? Yeah, so that has 11 electrons, but a net charge of what? Is it positive, negative? Like, what's our net charge of this molecule? Yeah, it's positive. So it's positive 1. So that means that we're going to, when we finish it, everything's not going to be perfect. We're going to have a net charge somehow, right? So in this case, which of these, nitrogen or oxygen, which of these are more electronegative? Oxygen's more electronegative. Awesome. So that means that it would rather be what, positive or negative? What is that? So if it's more electronegative, it would hold a negative charge more stably. Therefore, nitrogen would hold what charge more stably? Positive. So that means if we're going to have a positive charge, ideally we'd want to give it to the nitrogen, which can hold it better. So in that case, we said we had 11 electrons to use. So just by making bonds, we used how many? How many electrons are per bond? So then we used 4. So that leaves us with 7, right? All right, so wait, real quick. Do we have 11 electrons total? With the 2 plus, oh, so it's NO2, like 2 oxygens, and then the whole thing is positive. So it's like NO2 plus. Yeah. There you go. 17 total electrons. And then we have a positive charge, meaning that we lost or gained an electron. So we lost an electron. So instead of 17, we have what? There we go, 16 total electrons. So like we said, we used 4 just to make the bonds, leaving us with 12. So we have 6 electrons to use. If we were to not make any double bonds or anything, do we have enough electrons to cover everything's octet? No, we don't. So then we do want to make a double bond or 2. So let's try making 1 double bond here. And then if we go ahead and try to fill everything's octet, we just use 2 electrons to make that bond. So we have 10 left. So if we try to distribute that, we would get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have none left over. Is the nitrogen have a full octet? No. So then what do we need to do? Nice. So double bond the other oxygen here. And then now we've used up all our electrons. Does everything have a full octet? What's the formal charge of each of these oxygens? To what? So yeah, how do we calculate it? Let's use the easy way since we're already at this point. Let's go ahead and count how many valence electrons does oxygen have again? 6, nice. So if we want to find the formal charge for oxygen, we write how many valence electrons it has, which is 6. And then all we have to do is, not really a lot of math, all we have to do is 6 minus, so we said it has 6 valence electrons minus, let's go ahead and count every dot and every line connected to that particular oxygen. So we have 6 minus, 1, 2, 3, 4, 5, and 6. So we get what? 0. So the formal charge for that oxygen is 0. So any questions about that? Finding formal charge could potentially even be a standalone question on the ACS. So we want to make sure we're cool with that.
What's the thing for formula charge? Is valence minus
Yeah, so essentially, without using like the technical formula, this always gets you the right answer. You say, how many valence electrons does the object you have? So oxygen has 6 minus all the dots and lines that surround that particular atom. So in this case, it's got 4 dots and 2 lines, so that's 6. So 6 minus 6, and that gets you the formal charge. What's the formal charge of the other oxygen? Also 0. What's the formal charge of this nitrogen? Try using that technique to find the formal charge of that nitrogen. It's going to be the plus. Can what be negative? Yeah, you can have a negative formal charge. For nitrogen? So we got -3. We all agree with that? Cool. So how did we get that? We know nitrogen has a valence electrons. How many? 5. And then how many lines does it have around it and dots? 4. There we go. -4. And so we get what? Positive or -1? +1. All right, so we end up with nitrogen has a +1 charge. Does our molecule have a +1 charge?
You add them all up, right?
Yeah, exactly.
So it would just be a positive.
And so that lets you know that you drew the correct structure because our molecule has a +1 charge, just like our Lewis structure does. All right, so any questions as to how we got that? So now looking at the question, is that structure linear?
Yeah.
Okay, cool. So we know number 1 is linear. So now we got to test I3 minus. All right, so let's go ahead and do that one here where I drew the formal charges. All right, so I3, try to draw it on your own. I'm going to draw it up here as well, following the same logic that we just followed. All right, so that's the structure that you would end up with in this case in order to find the best Lewis structure for it. So how do we end up here? Why do we have so many valence electrons like around the middle one? The reason is because iodine has how many valence electrons? 7. This outer one has how many dots and lines around it? So 8. So it's got 8 things around it? 1, 2, 3, 4, 5, 6, 7. So it's got 7 things around it. Yeah, no, I know. I do that all the time.
Wait, but is your line, no, the line has 2. You just count the bond as 1.
Yeah, you just count lines and dots. That's how I like to think about it, so that you don't have to come across like this dilemma. Yeah, every line or every bond counts as 1.
Okay.
Yeah.
Because that's what I was getting confused on before.
I gotcha. Yeah, no, it's just so don't even think of it as a bond. Think of it as a line.
Okay.
Yeah. So it's 7 minus what? And that gives you 0. How about this one on the left? Same thing, right? So that gives you 2 out of 3 with a 0 formal charge. So is 0 formal charge good? Is that stable or not stable? Yeah, that's stable. So you want 0. So that's good. And then this middle one has a formal charge of what? Try that one out.
Wait, I have a question. Okay, so the line is 1.
It's just 1, yes. I know it's got 2 electrons in it. That's still correct. But we're just counting it as 1 line.
So when you do that type of problem, you have to count it as 1 line.
So what did we get for the formal charge of the middle one? -1. What's the net charge of our I3 molecule? So that makes sense that we get a -1. So in that case, this would be the correct Lewis structure because we have a net -1 charge. Now we want to look at it and say, is this linear? Yeah. Yeah, so it's linear. So this goes into the whole like Vesper stuff. So essentially this one, what kind of angle do I have between these two? 180, right? So that one would be linear because it's just got the 2 electron groups, right? And then, we move on to like trigonal planar. We move on to tetrahedral, trigonal, bipyramidal, etc. So looking at the second one, How many electron groups are around the central iodine? Think of that one carefully. How many electron groups are there? Okay, so I got two different, 9, 6. So think of electron group. An electron group is how many electrons in this case? How many electrons to make a group? 2. So how many lone pairs does it have? No lone pairs on the outside? It's got 3. So that's 3 groups. And then how many bonds does it have? Yeah. Here, I'll walk up here real quick. So if we look at it, it's not asking how many electrons are surrounding it. It's how many electron groups. So here we have one electron group, right, because we have a bond. Here we have a lone pair, so that's an electron group. Another lone pair, so that's another one. A third lone pair, and another bond. So we got, so 1, 2, 3, 4, 5 electron groups around it. So in that case, anybody remember what that electron geometry is called when we have 5? So like what comes after tetrahedral? Nice. So it's trigonal bipyramidal. But if you guys remember, when it comes to, when it comes to how many lone pairs make up those 5 electron groups, how many bonds, etc., that's when it comes into play. So in this case, this one is kind of like a setup problem from like the ACS people that's supposed to try to trick you. Because when we look at this, we look at, oh, that's got a ton of lone pairs, that can't be linear. So it is linear. So when you have 5 electron groups, and then 2 of them are bonds, that's linear. So just think about it in the terms of, you just have the 2 bonds, and essentially they make a 180-degree angle with each other, and all the lone pairs are kind of everywhere else. So that one would also be linear. So it's good to be exposed to like an example of something that's linear, but doesn't look exactly like these that only have 2 electron groups. Oh, and by the way, since I was talking about electron groups, this is just one electron group, even though it's a double bond, just like the single bond is one electron group. Because think about it, it's like bonded to one thing. So keep that in mind too. All right. So for now, we're going to skip 16 and come back to it if we have time, because it involves like drawing a pretty complex molecule relatively. If we don't have time to get to it, I'll have it drawn for you guys like when you guys go to look at the solutions and such. But for now, let's go on to 17. Which statement about bonding is correct? So look through those options, try to reason them, and then let me know what you guys think in a minute. And if you want, as you read them and you see one that you feel is blatantly wrong, let me know and I can cross it out. What?
No, I think I know the answer, but if anyone else is.
Oh yeah, no, go ahead. Tell me what you think it is.
I think it's
We got C. All right, so I got one option for C. Cool, cool. Let me know what you guys think as you find what you might think is the answer. Is it wrong? We can always cross out what you'd like.
actually
C might be wrong. All right, so let's see. So we got C and D might be wrong. So here, first, you tell me why you think D is wrong. Pi bond is what? Oh, it's the double bond.
So pi bond is
Yes. And then why do you think C is wrong now? All right, cool.
I don't know, I'm pretty sure a pi bond was 2 single bonds, and it just, I don't know, I just understood.
All right, I see. So that's good. We're all like applying concepts here. So we all just had like pi and sigma flipped around. So that's good. So if we look at it, if I have this right here. Okay, so now we got B. All right. Anybody want to go for like A or something? So we have like 4 options. It can't be C. Why? And what else? Nice. So if that's a double bond, we have 1 pi, and the first bond is always a sigma bond. So C would be crossed out by that logic because a double bond is 1 pi bond, 1 sigma bond, not two pi bonds. All right, so not C. So you change your answer to B right in time, right before we cross out C. That's good. Anybody else have another option they might think is correct? Yeah, I feel you.
It's like something's almost that way, they never.
Yeah, so I don't like the ACS. It's essentially, sometimes the questions like this one, for example, they give you like technical wording, right? And they don't expect you to know what the answer is. They expect you to know what the answer isn't. So if you can cross out 3 of them, you'll be left with one that you'll be like, I don't know what that is. It's just like an annoying kind of like a method that they have. But essentially, we crossed out C. That's really good. If we look at the other ones, let's see. A pi bond is twice as strong as a sigma bond. Looking at it this way. Here we have a sigma bond, and then above it we have a pi bond, right? Is this pi bond like, what, is it like twice the size of this sigma bond or something? Like, are they not both just lines, right?
Yeah, but isn't a pi bond 2 sigma bonds?
No. So a pi bond just goes on top of a sigma bond. Yeah, just like this one. So if you guys have like this, C single bonded to a carbon, what kind of bond is this? Yeah, it's a sigma bond. If I want to double bond it, what do I add? A pi bond. If I want to triple bond it, what do I add? Another pi bond. Okay, so
Can you just define, like, the sigma bond is a single bond, right?
sigma bond is a single bond.
Pi bond,
Yeah.
double bond.
Pi bond is the second bond of a double bond.
Plus pi.
Yes.
So technically it's not a double bond.
A pi bond, it makes a double bond, and it can also make a triple bond, if that
But
makes sense.
it's not a double bond.
Itself, no. Exactly. There you go. So
It is wrong.
B would be wrong. Exactly. Very nice. So by this logic here, we have either A or D to look at. A pi bond results from the sideways overlap of hybridized orbitals. So here we have a concept that I'll let you guys know. That'll let you know why D is incorrect. So a pi bond results from the sideways overlap. So if you guys just kind of memorize this picture, it'll make it a lot easier. When we look at a pi bond, it's two objects coming together like face on. So that makes a single bond. If you think about it, a single bond is stronger than a pi bond, actually. So if you want to write that just to know it, sigma is stronger than pi bond. So that right there is a concept. Why is that the case? Because if you look, this is a sigma bond here. It's head-on. Why is it shaped like that? It's all like really arbitrary, just electron stuff. The thing you have to know is it's head-on. So head-on, it's a strong bond. Now, when we look at a pi bond, if you guys remember, a pi looks like this, like an 8. Well, these are things that are bonding sideways. So a pi bond looks like 2 8s, and so they bond sideways this way. Okay, so if you think about it, something coming together head-on is going to be stronger than something coming together sideways. So this would be a pi bond, but now why is D wrong? It says a pi bond results from the sideways overlap of hybridized orbitals. So if we add a concept in there, do you guys remember a hybridized, like sp2, sp3, that kind of stuff? So essentially, only sigma bonds are hybridized. So if we remember this, pi bonds do not get hybridized, only sigma bonds get hybridized. So it's just another concept to add on there. So when we look at D, it says a pi bond results from sideways overlap of hybridized orbitals. Well, pi bonds are not hybridized, so how can they be the sideways overlap of hybridized orbitals? So they try to get you by saying sideways overlap, and then you might be like, oh, I know that pi bonds are sideways overlap, but then they throw that extra thing on there that makes it incorrect. So that leaves us with A, which, yeah, like, what the heck? A sigma bond has cylindrical symmetry about its bonding axis. Like, no one talks like that, right? So essentially, at best, I could say maybe if you want to memorize that, it's like, they're like cylindrical, kind of, how they come head on, right? It kind of makes like a cylindrical shape, but it's, for the most part, you kind of want to know what isn't correct for this problem. So yeah, several things to remember here. Only sigma bonds are hybridized. Sigma is stronger than pi. And then definitely, like for sure, remember head on versus sideways for P versus sigma, pi versus sigma, I mean. Any questions about any of those concepts there? All right, cool. So cool if I move on to the next page? All right. All right, it's number 18. So go ahead and draw C2H2 on your paper. Draw that Lewis structure and then answer number 18. All right, so I'm going to start drawing it as well. So what kind of bond do I have between the carbon-carbon? What was it? Is it like single, double, triple?
Is it triple?
Triple? Cool. Awesome. Nice. So yeah, we know it's triple because each carbon only has one hydrogen, so it has to have 3 more bonds to have a full octet, right? So it has a total of 4 bonds. So it looks like that. So off the bat, this CH bond is what, sigma or pi?
Oh, sigma.
Awesome. How about this other CH bond?
Sigma.
How about this first CC bond?
It has a sigma bond and 2 pies.
Sigma and 2 pies. Awesome. So anything past this first single bond is a pi bond. So the answer would be what? How many pi bonds and sigma bonds respectively?
3.
Awesome. So three sigmas, 2 pies. So that would be what? D?
Yeah.
Awesome. So yeah, those kinds of problems are the ones that you could potentially see as well. Notice we haven't done like a lot of math at all. Yeah, just remember you don't have a lot of time per question, so they don't give you a lot of math problems. All right, formal charge on the central atom of ozone. So let's go ahead and draw that one out. So we have ozone here. All right, so I'll give you guys that structure. And then you guys go ahead and find the formal charge on that central atom of ozone. So try to use what we just learned to find that formal charge. Find the formal charge? So remember, I'll get you guys started. How many valence electrons does it have? Oxygen?
Oh, sorry.
So we got 6, and then minus, try to finish it from there, and then we'll go over it again in a minute. So try to use what we did from the previous problem earlier with formal charge. Positive or negative? Awesome. So we got D, positive 1, because we do 6 minus how many dots and how many lines. So we have 2 dots and 3 lines, meaning minus 5 total, and we get positive 1 formal charge. Does that make sense?
Yeah, makes sense.
Okay. So essentially, be prepared to find a formal charge. It could be easy points, or it could be like unfortunate loss of points. So which of the following compounds would have the higher boiling point? Go ahead and look through that one. Let me know what you guys think.
So each dot counts as 1 and each line counts as 1.
Nice.
Interesting.
Yeah. I know, formal charge is odd. So yeah, 20 is which would have a higher boiling point. So boiling point, do you think a higher boiling point would mean that it's harder to break apart or easier to break apart?
Easier.
So easier, that means it would boil It'd be a higher boiling point? Harder, yeah. So think about it. It's like if it takes longer to boil, it's because it takes longer to break apart the bonds to turn it from liquid into gas. What? Okay, I cannot see what you pointed at. Come on. B, C. Okay, so I see what you're saying. So this one right here? All right, cool, cool. Because it's super long. That's good logic. So we know this one has high surface area. That's important. All right, cool, cool. Any other inputs? Yeah.
Can we think of it as like when you're cooking something, like when if it takes longer to obviously to boil it, it's because it took forever to pull apart.
Yeah, exactly. So that means it has higher forces holding it together, or stronger forces. So now try to use this, intermolecular forces. Try to think intermolecular forces, and then look at these examples and let me know what you guys think. So which one of these, essentially, are we looking for which one of these has the highest intermolecular forces or lowest? So if it's the higher boiling point, that means what? Higher or lower force? I got one lower. I got one higher. So which one is it? In the middle? So if it takes longer to boil, is it easier or harder to pull them apart? Harder. So is there stronger forces or smaller forces holding them together? So then higher boiling point equals stronger or weaker forces? Stronger forces. So try to think which of these has the strongest intermolecular force, and maybe we can even identify what it's called. And from now on, luckily, you can just remember like higher means higher. So higher boiling point, higher forces, they kind of just go hand in hand like that.
How do we figure out the higher intermolecular forces?
So what are the intermolecular forces? Yeah, so we got, that's one, dipole, dipole. I know, it's really ridiculous. So we got dipole, dipole, what else? Hydrogen, London. So what else is there? Is that it? We have one more, I think. Huh? Okay, yeah, that's another word. Good. So London / van der Waals. So we can definitely be able to recognize it both ways. Which of these three is strongest? So it's not three? All right, so not C. So which one's stronger then? So I got dipole, dipole. All right, cool. So which one of these would be strongest then? So what would be the answer? Between 3 and 4? So what is the difference between 3 and 4? Would you say that this molecule has a dipole? So I got to know? And why? Let's draw it. Let's draw it. So we have CO, right? Carbon bound to an oxygen. Let's not even draw any electrons, any of that, because we know we just have those two atoms, right? So would you say that these have the same electronegativities? Yeah. So which one's more up and to the right? Oxygen. So oxygen is more electronegative, right? So by that logic, we can kind of safely assume that this molecule is polar, because oxygen is more electronegative than carbon, right? So that means that if it's polar, that means that which one's more partially negative, carbon or oxygen? Oxygen. So that means that carbon's partially positive. So we draw the dipole arrows. Do you guys remember seeing those? So it's just called a dipole arrow, and this plus is essentially saying, hey, this carbon has a partial positive, and the charge, the negative, moves towards the oxygen. But all that means is that this molecule right here is polar, right? So if it's polar, it's going to have dipole-dipole, because essentially all these polar molecules are going to attract each other. That's why it's called dipole-dipole, because it's one molecule with another. So this one would be a dipole-dipole interaction, right? Now, anybody remember, is hydrogen not the strongest intermolecular force, hydrogen forces? So, yeah, London. So this is the weakest. This one's medium, and this one's strongest. There we go. So yeah, it's not dipole. And you know why? Because a good way to think about it is this one has a hydrogen bond. Why is a hydrogen bond stronger than a dipole interaction? It's because a hydrogen bond has dipole interactions, and then it has the hydrogen on top of that, making it even stronger. So think about it. Water, is that polar or nonpolar? What is it? Water. Polar. Water is polar. Nice. Water is polar. That means it has dipole-dipole. But the main thing it's known for is having hydrogen bonding because it's stronger, so it adds on top of it.
What are the four, like the only ones that have
The
hydrogen?
3, good.
What are
That is a 3. Okay, so we got F, O, and N. Yeah. Yeah. True. So we got the 3, F, O, N. So in this case, is option number 4, does that have hydrogen bonding? Which one? Yeah, because look, because we said only these 3 can make hydrogen bonds, not carbon, right? So those, even though it looks gigantic, these top 2 only have London, so they're actually the weakest. And then this one has dipole-dipole, we said, because it was polar. And then NH3 plus has hydrogen bonding because it's got a nitrogen connected to a hydrogen. All right, so by that logic, then our answer would be what? Nice. So yeah, definitely just remember that hydrogen are your strongest bonds. That's what they tend to test. They're never going to ask you what has the lowest boiling point. It's always like what has the highest, which of these forces is the strongest. So just remember the FON and the hydrogen bonding, really important. Any questions about that? So yeah, just your intermolecular forces. One of 7,000 topics to know, it seems like, for this test, right? I know. It's so weird, like two semesters into one, right? I never understood that. Luckily, that's why I said, like, if it ever goes really badly, professors will like curve and do that kind of stuff. For chemistry too, you also take an ACS for Chem 2, and it includes like everything as well. But my professor curved that so much. It like I'm talking like I'm like being recorded right now, but it's like it curved me like it went so badly that I got like a 50, and it curved me to a 100. 99, a 99. I'm not joking. So we'll see if it's like if it's not fair, then they tend to maybe potentially help you guys out. She doesn't have to, no. All right. Oh, okay, hey guys, hey, I'm being recorded. Thanks. All right, so how many total orbitals are present when n equals 4? Yeah. So think of it now. Think of it this way. I'll give you guys this hint. Wait. I'll give you guys the hint. When n equals 4, we can have, if you guys think about it, n also tells you like the row on the periodic table. That's another thing your quantum number tells you. N also lets you know what row. On the row 4, you can have 4s, you can have 4p, 4d, and 4f. So if, yeah, so add them up. S has how many orbitals? Orbitals. There we go. 1 orbital, 2 electrons. So 1. P has how many? Close. 3. So P has the 3. D has how many? Now from now on, just they each add 2. So D would have how many? And then F would have? Yeah, so after, if you just remember S, you'll know that plus 2 will tell you all the other ones, if that makes sense.
Wait, how do you, I thought S would be 0.
So no, it's not that would be the L number for S. So how many orbitals it has is just referring to whenever you draw it with an electron on top, like for S, is how many lines are above it. Yeah, so those are the orbitals. So in this case, yeah, if you add all those up, you get what? Nice. So that's what that one's testing right there. So 4, that's why it says n equals 4, like it's on purpose. 4 is the very first n that includes all SP, D, and yeah, exactly. So if it said n equals 3, it would only be SP and D, and the answer would be 9. Yeah. So, all right, and then back to a little flashback to like beginning of the class. Wavelength of one of the spectral lines of helium is 492. What is the energy of a photon with this wavelength? So go ahead and I'll tell you guys this much. Energy of a photon equals h times nu. If you guys remember nu, h is, what is h, by the way? What do we call that? Who remembers? Something constant. What constant? Nice. So h is Planck's constant. Anyone remember the value for that? Yeah, right? I actually think they give you like constants and stuff on the ACS. Yeah, I'm pretty sure they do, from what I remember. But you know, you can never be too safe. So I'll start you guys. Maybe muscle memory will kick in. 6.626 times 10 to the what? Close. Negative what? Close, 34, yeah. Negative 34. They give it to you? Yeah. Nice. So times 10 to the negative 34. And nu. What's another word for nu? We have wavelength, and then we have what? What's the other thing that a wave can have? That's not wavelength, it's free. There you go. So that is essentially tells you the frequency. But do they tell us the frequency in this problem? What do they tell us? The wavelength. You see, it says, I know that because it's like, the word is like 20 feet away from the number. So they tell you the wavelength. What's the symbol for wavelength? The weird what? Yeah, exactly. So it is. So we have a formula that goes nu, or frequency, equals c over lambda, with lambda being the wavelength. So this is the chapter with like all the weird symbols. But essentially, what is c? What do we use for c? It's the speed of something. What is it? There we go. So c is the speed of light. And what is the value of it? I'll tell you guys. 3 times 10 to the what? 3 times 10 to the something. Is that one given to you? Oh, wow. So I'll give you guys this one now. So maybe like you guys, it'll just click now. So it's 3 times 10 to the 8th. So that's the speed of light. So 3 times 10 to the 8th.
Oh, they give you that C. It says C equals 2.998 times 10 to the 8th.
Oh, yeah. So they just don't round it. Yeah. Okay, but so it is given to you on the ACS. That's good. Huh?
Yeah, they give us both, and they give us the last one that she made us memorize.
Which one?
She made us memorize.
Oh, the R?
Equals
Yeah.
0.0821.
Okay, that's good. So now that's awesome. That's really good. All right. So now we know the wavelength. We know the speed of light. So with that, we can find nu, which tells us what? Awesome. And then with the frequency, we know h, so we can find the energy of a photon. So try that out. It's weird. It's actually, and here's actually a really big part of this problem here, is speed of light. What unit is it measured in? Who wants to tell me? Meters per second. What did they give us our wavelength in? Nanometers. How can we mix meters per second with nanometers? You have to convert it from nanometers to meters. So 492 nanometers. We got to convert that. So take your calculator out if you have it. We know that this is the part where a lot of people mess up. So if we're going from nanometers to meters, we know that on the top we're going to have meters. And on the bottom we're going to have nanometers, right, to cancel. So we can say 1 times 10 to the what? What is nanometers? Nice. 1 times 10 to the 9th nanometers equals how many meters? 1. Very nice. So then go ahead and tell me what that gives you so we can continue the problem. Oh, wow. All right, then anybody get like the scientific notation version? Something to the what?
I could do it.
Okay, awesome.
So it would be 4.92 times 10 to the negative 5.
Thank you. So 4.92 times 10 to the negative 7th meters. So that right there is important because that's the one you need to plug in there. So go ahead and try that. C over lambda with the values we just got to find frequency to then find the energy of a photon. And I know this was like, well, I know we have like a lot of Chem 1A stuff that was a while ago, but this was like beginning of the semester, like potentially even like lecture 1 or 2 stuff. So I know it's been a while, so make sure you get some practice with that real quick. So energy of a photon would equal what? Let me know what you guys get for your final answer. But yeah, like realistically, this is like as math intensive as it'll get on the ACS, honestly.
Oh, really?
Yeah, yeah.
Will it be kind of easier?
That's the thing. So it's like they make it to where you don't have to do much math at all, but you have to know a lot of concepts. So it'll be like, for example, like earlier we were doing like moles and stuff. Like you don't have to do a whole stoichiometry. You can just look at the equation and say like, oh, if I have 1 mole of this, that means I have this many moles of this. So it's like a lot of conceptual stuff. So yeah, the calculator does not get used much like at all, from what I've seen in the past. Who knows?
One that like ended up to be 15 divided by 2, I spent like 30 minutes like trying to like write out like the stuff, and it's just like you divide.
I know, and then can you imagine like it's a 55-minute test? So yeah,
That's so scary.
I gotcha. Did anyone get an answer? 4.04? To the negative what? Awesome. Sweet. So then we've got an answer there. So, you know, that's like a general pathway. The most important thing there, other than converting nanometers to meters, is knowing the relationship between V and lambda. So frequency and lambda. You just got to know that they're kind of inverses of each other like that. But yeah, so we're kind of running low on time. So let's go ahead and try to quickly answer number 24 and 25, which don't require a lot of conceptual stuff. So which of the following is not an electrolyte? So yeah, when we're thinking of electrolytes, we're thinking like a while ago. So any of these particularly stick out right now as not an electrolyte? So how about A, H2SO4, is that an electrolyte? So no, why not? So what is H2SO4? Is that what is like a base, acid? It's an acid. So from now on, just think acid will be electrolyte. A base will be electrolyte as well. Essentially, anything ionic can be an electrolyte. Whether it's strong or weak, that's different, but I don't believe that, you know, it'll be that in depth. Just understand anything ionic's an electrolyte. Do any of these stick out to you as not being ionic? Because essentially, one of these things, when you put it in water, will not dissolve into ions. So for example, if I put D into water, I'm going to get K plus ions and some CO3 minus ions. right? So that's an electrolyte. H2SO4, we have sulfate, SO4 2 minus, and H plus ions. So that will be an electrolyte. Over here, does Na make an ion? Na doesn't? Yeah, Na, it makes a +1, right? So that's a metal. Over here, CH2O. Is there a metal here? So there's no metal, right? Is this an ionic bond at all? No, so this right here, CH2O, can you see any ions that would come out of here? Like, do we know like a CH plus ion or something like that? No, so all of these we can kind of see. We know K plus, we know Na plus, we know H plus, we know SO4 2 minus, like sulfate. Here, like that's, I can't think of an ion with any of that, right? So that's how you would know that it's not an electrolyte. Try to keep it as basic as if it's not ionic, it can't be an electrolyte. So it's like sugar won't dissolve in water versus salt, which does. So the answer is C. And yeah, we're just about out of time. So we didn't have time to finish the last couple lines. We got to be really strict with like when we end, unfortunately. But if you guys look on the website by the end of today, it'll all be posted with all the answers, even the ones we didn't get through, like the earlier one with the molecule. I'll have drawn it and stuff. So yeah, look out for that later. Thank you guys for coming. Oh, and then one thing, I believe I got to pass out a quick, if you guys wouldn't mind. I think we just have to pass. Okay, oh yeah. That'd be awesome. Yeah. So here you go. This is just a quick like little survey. You guys